record to the cloud. We should be up and rolling. It's recording. Screen 2. And you still see the PowerPoint now?
I can still see it, yeah.
Okay, perfect. All right, so I can clip this part off in the beginning, so we're still good to go. 1, 2, 3, we're ready. Hello, my name is Jade Denson. I'm the Director of Member and Community Engagement with the Minnesota Technology Association. And today I'm excited because we're going to cozy up next to the fire and learn more about machine learning stories and case studies from one of my favorite data scientists, Mr. Will Armstrong. Will is going to share the examples and ways that Cargill is using machine learning to transform the work that they're doing in the agriculture space. So Will present for about 20 minutes or so, and then we'll pull up a seat next to the fire and do some Q&A, and he'll answer some questions about how they've deployed machine learning in 2 really, really cool ways that I'm excited to share with you all today. So without further ado, let's cozy up next to the fire. All right, so Will, let me get your deck queued up and then we should be good to go.
Awesome.
Okay, I'm ready when you are. Go ahead, take it away, Will.
Absolutely, absolutely, and thank you for the great introduction. I feel metaphorically warmed, if not physically warmed, by our virtual fire.
That's the goal.
Right on, right on. So yeah, so the title of this is Morals of Machine Learning Stories. Jade, when you kind of asked me, if I could tell our community a little bit about some stories of how Cargill is using machine learning, I thought, well, every good story should have a moral to it. I'd like to talk to you about a couple of examples, ways that the data science team in Cargill are using machine learning for a couple of different applications. One of them is sort of very early, very kind of in an R&D kind of phase. And the other one is something that's very much in production and something that's being used today. If you don't know Cargill, we're a large private agricultural and manufacturing company, and we also have a fair amount to do with the nation's and the world's food supply. And animal welfare is something that's very important to us. And so one of the stories that we'll be talking about is how we can use machine learning to affect an outcome that increases animal welfare. But first, we can go to the next slide. First, a little bit about who we are. So we are the Cargill Data Science Team. We're part of Cargill's larger research and development group, and this includes chemical engineers, chemists, scientists working on processes. This includes experts in industrial engineering and process modeling and control. And it also includes the data science team, my team. We are experts in math, computer science, engineering, statistics. Data science continues to be at Cargill as much as anywhere else, a multidisciplinary endeavor. We have people with that come to us with a variety of backgrounds, from computer science all the way to economics. We like to code in a few different languages. Really, it's the language that the data scientist is most comfortable in. Languages like R and Python, and we use tools. We're an AWS shop. We use tools like SageMaker. We of course use GitHub for code collaboration. Where we try to be consistent, and this is sort of the general strategy, is we like to give data scientists freedom to use the tools that they're most comfortable with in doing research and developing models, but we like to give them kind of a hard target to hit when it comes to putting them into production. So we at the end of the day, in terms of the tangible things that we're building, that's predictive microservices that leverage the AWS stack and the various open source technologies that's based on. This is kind of a picture of who we are. We're in 3 countries. We have an office in the Twin Cities here, one in the Netherlands, and one in Brazil. And we also partner with both the University of Minnesota and University of Illinois at Urbana-Champaign. We kind of have, so the team, we kind of say, okay, these are the sort of like named capabilities that the team has. They're all pretty broad, but just to give kind of an idea, both to you and to the people in Cargill that we support, kind of what we do. You know, this is the list of our named capabilities. We do optimization and simulation, computer vision. Both of the projects that I'm going to talk about today are computer vision projects. Excuse me. We do forecasting, we do customer and pricing. This is something that we partner with our customers a lot. We do, most of Cargill is, as you would expect, business to business. So we partner with retails, people that put the products that we have a hand at some point in the supply chain on the shelves. Smart manufacturing, that is kind of theories of where AI kind of comes into automation and the theory of control systems. Molecular data science, something that people think is really interesting, have a lot of questions about. It is pretty cool, but it's using, it's the sort of the nexus between, it's exactly like the nexus between artificial intelligence and synthetic chemistry, right? Like how can we use AI to come up with new templates or designs for molecules that we can then synthesize in a lab. We can move to the next. So the first project I'd like to talk to you about is something that we call Project Grade, and it's to do with grading soybeans. And I'm not an expert in soybean farming, so I'll do my best to tell you kind of what the process is, and then we can talk about how machine learning comes into play. We can go to the next slide. So yeah, so the process is, so a lot of the soybean farming that Grade connects with is happening in Brazil. We have independent producers that farm and harvest soybeans, and they're brought into Cargill's processing facilities in shipments on trucks and rail cars, and there's a certain intake process there where where an inspector will take a few samples from the shipment, measure things that they can measure in aggregate, like the humidity, the mass, but then there are some things that you actually have to look down kind of like bean by bean to see. So we take samples from different parts of the shipment, literally put them out on a table, and a human inspector picks up each one and looks for certain signs that tell us the conditions of the soybeans, right? If they're burned from the friction of being put into a pile and shipped, if they've started to ferment or mold. We can go to the next slide. There are certain difficulties with this process. One is that we actually need to train human assessors on how to do this and what sorts of things to look for. And we run into the situation where, some of this is seasonal labor. And so the value of the investment in the training process can be limited by that. And also the process can take a really long time. If sort of few flaws are discovered in the soybean assessment process, it can go very quickly. Just a whole shipment might take 3 or 4 minutes, but if they start to see signs that the quality is perhaps not ideal, then the assessors actually have to start cutting the soybeans open and inspecting them on the inside. And if this happens, the inspection process could take 20 to 30 minutes. It can really slow things down, and we've even had situations where we have queues of deliveries forming outside waiting to unload. And there's a pretty high impact, right? This process both determines the price of what the shipment is, the price that Cargill will pay for the shipment, and it also determines kind of what we can use these raw materials for, whether they're going to be ground, processed into flakes, whether we'll extract oils from them, these sorts of things. We can go to the next slide. Also, unsurprisingly, there's the consistency is important, and the sort of the human element, based on the studies that we've done, we've kind of found that you can tell based on what the outcome is, you can almost kind of tell which assessor was doing the grading, and certainly you can tell what region the grading was done in, because different regions, assessors trained in different regions look for different things, and so kind of our goal with bringing machine learning into the mix here is both to reduce the amount of time that it takes to assess these shipments, but also to try to drive some consistency. And so what grade is, it's a computer vision algorithm that literally when the soybeans are kind of cast onto a table and a human assessor goes through and looks for soybeans that have certain qualities that exhibit certain conditions, the question is, can we take a photograph and can we use computer vision to do that assessment? And like I said, the outcome is to reduce time, to reduce variability, and also to influence the training process as well, right? So if we can understand, like I said before, part of the process is if you see certain signs, you actually have to physically cut the soybeans open. Can we get some insight into what those signs are, right? And maybe try to both enhance the human assessing process and also maybe tell people how, which things to look for before the soybeans are cut open, right? What kinds of signs on the outside can tell if they're maybe starting to mold or ferment on the inside. We can go to the next slide. So how it works, how the grade computer vision model works, it has two pieces. One is a localizer and one is a classifier, right? So it's the first problem it solves is where, it takes the image of soybeans on a table. What part of the image is a soybean, or where are the soybeans in the image? And then it carves up that image, ships those over to the classifier, and the classifier looks sort of bean by bean and comes up with the inference that the classifier model makes is what, one of, you can see them on the slide here, one of about 10 different conditions. The localizer, as with a lot of computer vision stuff, is based on a public open source model. So we used what folks call transfer learning, where we took an open source object localizer called YOLO version 3, and we retrained it, only allowing the last layer or the last couple of layers in the neural network that is YOLO version 3 to vary based on the training inputs. So long story short, we took something that's very good at localizing objects within an image for lots of different objects and made it good at localizing soybeans in a 2D image. The classifier, architecturally, not really that different from everyone's first example for what has kind of become the hello world of computer vision, the task of recognizing the handwritten digits in the public MNIST data set. Architecturally, very much the same. We have images that come through the localizer where there's good on-center image of each case, and we use a multi-layer custom convolutional neural network to make an inference about the condition based on the localized image. We can go to the next slide. This is kind of high level what the learning process is. This is, you almost can't avoid, when you talk about machine learning, automation, artificial intelligence, you can't avoid the conversation that people have anxiety about humans kind of being replaced or removed from the process. This is really intended to be a tool to help the humans do their job faster and better and more consistent. We actually have a smartphone app that the assessors use to take a photo of the inspection table, upload that photo to the cloud, to a SageMaker instance where an inference is made on that photo, and then the results are shown back to the assessor, and then the assessor, as they're assessing, as they're grading it, they can mark how well the model did, right? They can say, well, they can kind of go case by case and say, this one was labeled correctly. Maybe I don't know if that one is labeled correctly. And kind of what I'm going to get into a little bit in the next couple of slides here. We're actually capturing how well the model is doing in real time and sort of continuously collecting data, right? Adding to the body of data that we used as the ground truth when the model was developed initially. You can go to the next slide. Thank you. So how did we come up with the ground truth? Really, this story, the story of this project is, we kind of did it the hard way. And there really wasn't a way around it. We started with, we had to go through the manual, very labor-intensive effort of, taking pictures of lots of soybeans in various conditions. We did use some crowdsourcing for training both the localizer step and the classifier step. The classifier step, we also took lots of soybeans, right? And we arranged them in a grid on a table, and we labeled each part of the grid, took photos of them, gave them each an ID, and then had people literally, cut them open to get a high degree of confidence in that ground truth. So we essentially took a bunch of soybeans and did the maximum amount of assessment on each one of them individually and then to get a label at the end of it. And then we also, as one should generally with any computer vision project like this, especially when classification is the key, we took this corpus of labeled image data and augmented it, which literally means just kind of messing with it, right? Messing with orientation, messing with lighting, changing the contrast, white balance of the images. The reason for this is really to help the algorithm really get at what are the differences from soybean to soybean, right? And kind of prevent it from picking up on things in the image that may be a red herring, right? That won't directly lead to that aren't directly pertinent to classifying what the actual condition is. We can go to the next slide. So if this story, I think, has a moral, I think that's it. We were lucky in that we had the buy-in and the investment in time to come up with really good labeled data, and also really balanced data too. And this, I would say, is the main thing, that leads to how well this computer vision model performs. For most of the categories, it has a balanced accuracy of over 90%. Now, there are some computer vision tasks, I should say, where balanced accuracy of around 90% is failing. This one isn't one of them for a lot of different reasons. And there is one category that the model quite hasn't learned how to identify as well as the rest. But the other, but it's hard, right? Data acquisition. There are most projects, I think, or at least most machine learning projects that I've worked on. You're kind of stuck with the data that the process has generated, and one doesn't necessarily have the luxury of going out and measuring directly to come up with a good corpus of balanced data under experimental conditions. And I think this project succeeded in large part because we had the buy-in to do that. And sort of the last lesson from this, and I didn't really touch on it yet, it's really important. The choice of tools that one uses are fairly important. And I think the biggest thing that one should be thinking about and trying to answer, okay, what technology and tools should I use, is more, what is the documentation and what is the support of the community for people working in those tools? I think that's more important than the technical capabilities of the tool, because when you're stuck, right, the more documentation, the more community, the more people using that tool, the larger the body the more people who can help you with it, not to put too fine a point on it. So The next project that we're working on that I want to talk to you about, we call it Chicken Check. This is kind of, this touches computer vision a lot too, but this one's also kind of more multidisciplinary than grade, which is to me a pretty pretty boilerplate use case for computer vision. We can go to the next slide. This started with some of our customers and partners, people that we directly support with our business. McDonald's actually put up a good amount of grant money to people to develop automated, basically some kind of automation that can give early indications or get a read on animal welfare, specifically for broiler chickens. The people that won the grant, the people that got the grant money, pretty much all of their solutions involved in some way computer vision and also computer listening. And it turns out that this is something, like I said, for us, it's kind of early. We're in the R&D stages, but this is something that, when we heard about this, it was like, well, Cargill's kind of been working on this for a while too. And it's something that's really important to us and also really important to consumers, right? Some survey, which is cited here, came up with the number 58%, right? 58% of customers want to see, want to see some evidence that the people that are involved in food production care about the welfare of the animals that come into our food supply. We can move to the next slide. So kind of broad strokes, what the project is literally putting microphones and cameras in chicken coops, collecting data and mining those data, the audio and video feeds, for things that we can hone in on as indicators of animal welfare, right? So the cameras, we can, the key thing that we're looking for there is movement, both the movement of the flock kind of as a whole. And then for the microphones, the key thing, we're looking for things, vocalizations that we can train an algorithm to recognize as being distressed or not distressed. And then the outcome that we're trying to measure, we can go to the next slide. The key outcome that we're trying to anticipate or predict with this is mortality. So if you were to sharpen up what the machine learning task of this project is can we anticipate or predict chicken mortality from audio, video, sensor data, and also like one-dimensional sensors that we have in there too, right? Things like temperature and humidity. And the outcome is, to put it simply, happier chickens. Are there things that we can identify that are early indications of changes in flock health that will down the road have an effect on mortality? And then we also, we want to decrease the mortality and increase animal welfare. We can go on. So the computer vision piece, again, much like grade, we started with something open source, an object tracking framework called OpenCV. Well, OpenCV is a general computer vision framework that offers some object tracking functionality. And we were using it to literally say, like in the video feed, track objects that are moving. We actually had a somewhat difficult time tracking like individual chickens or training computer vision algorithms to recognize individual chickens. We can sort of do that with cows, but with chickens, it's proving a little bit more difficult. But once we can localize and identify a moving object in the video, in each frame of the video, we can go to the next slide. We can track the movement of their centroids. And this really, how we're thinking about the computer vision piece of this now, what this does for us is it gets us, right, a 2D or a series of 2D frames that are raster data into more of a movie about about where, frame to frame, vectors of, frame to frame sort of movement over time. And then we can start to think about, we can go to the next slide. We can start to think about, do we train, do we, make these like the input layer of other deep neural networks? Kind of where we started was taking just kind of univariate measurements of that movement and how it changes over time. So like the mean amount of movement, the skew, the distribution of movement. Also things like curl and divergence. If you remember your vector calculus, are basically, sums of like sort of outward movement or swirling movement, vorticity, and kind of what we learned from this is like, yeah, each one of those kind of univariate measurements of movement over time, they are important and they do have an impact. And each one of them has about as much impact on the, I guess what you can think of as more traditional kinds of measurements of health, which are things like, how much do they weigh? What is the humidity and temperature of the environment they're living in? How much water are they drinking? Those sorts of things. We can go to the next slide. So if this story has a moral, it could be, always be checking against baselines, right? Because sometimes the outcome that you're trying to predict or anticipate might not necessarily only come from something very complicated like a computer vision model. Right? I mean, it's certainly, that's interesting work. And we think that there's more, and I say this project is kind of in an R&D phase. We think that we can definitely take the analysis, the really unstructured kind of deep learning analysis of the video and the audio data farther. And I can say for, in terms of audio, right, we're considering approaches where we kind of figure out how to come up with vector embedded representations of vocalizations that we can cluster and then work with experts in animal behavior and animal vocalization and kind of tell us what these clusters of vocalizations mean. But it could be that, you can do a lot just by measuring some very simple things. And then the other key moral here is if you're, so I should back up because this one needs a little bit more context. So the outcome that we're trying to predict and affect here in this case is mortality, and this is something that people are already working on, and that creates a bias in the data, and it's a bias that you. Being a well-trained statistician or data scientist, you hear that and you're like, oh, I want to remove the bias from those data. Well, this is something that that we can't ethically do and nobody wants to do, right? We're trying to affect a certain outcome, and the data that we collect are reflective of that bias, the bias in the process itself. And so as we're going through and doing this analysis, we have to really be aware, right? Like this is the process that generates these data is not an unbiased process. And that means it's more difficult to find signals predictive of the outcome that the process is biased against. We can go to the next slide. So really interesting, more interesting to me than stories about how machine learning goes right is kind of how it fails, because how it fails tells you more about. I think there are more lessons to be learned in from how machine learning goes wrong than how it goes right. These are some very famous cases. They've been in the news from a few years ago. I won't necessarily go through each one. And to all of these institutions' credit, once they made the news, they did take corrective action. I shouldn't have to explain why each one of these are horrible or outcomes that you wouldn't want. But the thing that I would say in each one of these cases, it was really like the sort of machine learning piece of it, what was doing exactly what it was quote unquote supposed to be doing, right? It was finding, inferring relationships in the data that it was given, and what I think this highlights is, kind of the same thing that I was saying, the moral of the chicken check story, right, is that, data is you can't analyze data independent of the process that generates those data, and if that process has biases, and you put that before, quote unquote, the algorithm, whose job is, and it does this well, to find relationships that it can use to infer an outcome, it may well just end up learning the biases that are present in the data that it's given. We can go to the next slide. This is a slide that I like to show. I think, projects that involve machine learning, they have a maturity curve. There's a, and you can think of this as being macro and microcosmic, right? This can apply to a whole institution. It can apply to project by project basis. And very briefly, because I know we said about 20 minutes, and I think I'm just about 5 minutes over right now, because I do want to leave time for questions. The process that any machine learning project kind of goes through, right? It starts with getting good data. And good data, kind of as I was alluding to, you don't always have the luxury of being able to generate unbiased data, but at a minimum, right, one should know. And it's really part of the job of the data scientist to interrogate this, right? Interrogate the process that generates the data, understand the biases and flaws that are present in it. And that's kind of what I, consider having, quote unquote, having good data really means understanding the data really well. And then from there, right, you can do analysis that's descriptive, synthesize it, right, kind of understand the story that the data is telling. And then the next stage is putting that into a framework where you can be predictive, kind of anticipate what will happen. And then the top of the maturity curve is being prescriptive, right? How can I use these data? Well, first, how do I understand the data? Second, how do I understand what the data tells me? Third, what does the data tell me is going to happen in the future? And finally, what is one to do about it? We can go on to the next slide. I would say, if you're approaching a machine learning project, there are two questions that should be top of mind. First question is, what is the task? What are you expecting the algorithm to do? The more specific, the more one can kind of firm this up, I think the better outcome, the better the outcome will be. And then the second question is, do we have the data to be able to answer these questions? And if not, how do we get those data? And then how well do we understand it, right? Do we understand its biases? Do we understand the process that generates those data? You can go to the next slide. And that's the last slide.
Awesome.
And I wonder if I lost,
Will,
I didn't lose you.
Sorry, what'd you say?
I said I was wondering if I lost your audio. I didn't, but I see now that I didn't.
No, now it's time to put you in the hot seat and ask some questions.
Awesome, I love it.
Awesome. So I kind of want to start in a little bit more of the weeds of the technology components of machine learning stories you talked to. So you did a great job of giving us sort of overarching storytelling about the two examples that Cargill is working on from a project perspective. Can you talk a little bit more about like frameworks and toolkits or training sets you've used or different platforms you've used? Can you go a little bit in the weeds of the technology component of the two examples?
Yeah, absolutely. So kind of like I said, right, the way that I like to think about running a data science shop is really like when people come in, data scientists, machine learning engineers, when they come in and we give them problems like, hey, can you, knock up a model that like does this task for us? I really don't like to be prescriptive at all, right? I'd like to say, whatever you want to use, whatever you're most comfortable with, whatever you know most about, through that sort of design phase. And I think this is another point that's actually not in the slide deck that is really important to hammer home, right? People think of doing supervised learning kind of like as a big ball of wax, and you really like can separate, or one ought to separate out in their mind, like designing the solution and then implementing the solution, right? So designing the solution is doing things like, getting labeled data, training a model, testing it out, trying different kinds of models. And in that camp, I don't like to prescribe technology for people to use, right? They should use whatever, right? But on the other side, right, you've got to, you can come up with the best model in the world until you put it somewhere. It's not helping anyone, but the data scientists feel like, oh, what a clever boy am I? I've come up with this great model.
Right.
So that's when I think one should be really prescriptive, right? So to answer the question that you actually asked, what are the tools? So we have a stack, right? It's all based on AWS. We have a template that we actually designed that uses it's Python, and it uses the Python API for Amazon SageMaker. It lives in the larger what Cargill calls the Cargill Cloud Platform, which really, like most open source stuff, it's based on technology that's kind of like more open source as you go down the stack. So, and I'll say, like, it's Kubernetes, right? Kubernetes to manage a bunch of Docker containers. So I say, okay, we make predictive microservices. A predictive microservice is a Docker container that has some Python modules inside that provide usually a REST API. And we have one of the data scientists on our team, a gentleman by the name of Victor Caldas, very capable man. And I feel like giving him a shout out. He actually wrote a template for us to kind of like alleviate the burden for the rest of the data scientists on having to learn, Python dependency management and containerization and stuff. So we have a template that has environment files, Docker files, pretty much what you need to, throw together, a couple of Python modules, that talk to SageMaker instances, right? Oh, and when we sort of bake, or some people say pickle, right? Once the model's fully trained, it gets baked into a SageMaker notebook, right? And so then we have a Docker container that talks to a SageMaker notebook, provides the API. So request for inference comes in from the API. The data that it needs are stored. The assets are stored in S3. Talks to the SageMaker notebook, gets the assets that it needs, returns the inference, and then the answer, the response to the API request is fulfilled once that's done.
Awesome. So now that you've kind of set the stage of what goes into the technology pieces, which obviously we can't get a full deep dive into everything, but can you talk a little bit about, like, what were the major challenges technology wise? Like, what are some of the things you ran into beyond like the thematic things related to deploying machine learning? What were some of the technical challenges of getting this done?
Sure. Yeah. And I would say the main challenge, as with a lot of things, the main challenge is I guess one of education. Because when we work with the template for these kinds of things, it's kind of like, it's kind of different and unique and complicated in one sense, but also like really simple in another sense, right? It's really simple in that, like, okay, well, we just want to be able to stand up like a microservice, right? And we want to give our team of data scientists kind of the ability within the framework and the rules of our organization to do that, and to be empowered to like do that on their own, right? And then you kind of get into this sort of unique, I will say just unique institutional situation where it's like, well, wait a minute, like, you guys are not part of like IT, but you're developers. And I would say that is a big challenge. And it's not, and I would say not just at Cargill, right? But the most of the institutions that I've been at over the years, right, seem to always be trying to decide, whether data science is part of quote unquote the business or part of quote unquote IT. And I would say it's neither, right? It's a third thing that kind of straddles both and needs strong connections in both. So to answer your question, okay, what are the main challenges? I would say that was the big one, right? Like getting the buy-in to sort of be allowed to participate in the process and use the tools and technology that Cargill uses in software development kind of for our own ends. Of course, the other challenges getting kind of on the other side, right? If it's a third thing if data science is a third thing that is, you should be equally embedded in both. It's getting our data scientists kind of plugged in and trained up on the business, on the operations, right? So that they can understand the data that they're looking at and actually physically getting the data too. Cargill is a very large company and it's made out of a lot of different business units. And one challenge is, and I'm sure this is not just Cargill, right? Not always having a single source of truth for the data. And I'm sure you've heard this before too, from other people that you've talked to as well. And then also like again, this goes back to the challenge of like education. I would say, making our partners understand kind of that what we need is, when we say that we need data, what we really mean is we need like a connection, right? We need to be able to build pipelines into existing data sources. And we're not, for example, just looking for like a one-time extract or a dump, right? Or the ability to look at a dashboard. Because a lot of people, when they hear these questions or hear like, oh, we need data, it's like, here is some data and it's a chart. And it's like, that helps someone maybe understand what the data is, but it's not like the data itself, and there are things that we're looking to tease out, that one, don't just come from one particular visualization. And also, we can say, and don't get me wrong, like in that kind of first phase where we're researching, trying to develop algorithms or at least, like a template or a framework for an algorithm, a dump is fine. A dump is great, right? A snapshot, right? In the design phase for a machine learning thing, you can spend lots of time with a snapshot, satisfying yourself that you've got the best kind of model, tuning the performance of the model on that set of cases. But at some point you're going to have to pivot and you're going to need live feeds and you have to answer all of those questions about like, one, I'm going to stand up a service. How do I get the service plugged into the inputs that it needs? And two, how do I get the output into the hands of people that need it?
Awesome. That's super, super helpful, Will. I think I have more questions than we have time for, but I do want to squeeze in two others. So hold tight as best as you can. I'm going to maximize our hour together today.
Yeah. And I should tell you, I actually don't have a hard stop. So
okay.
Let's get through the material that you want to get through. And I will do my best.
Okay.
And if I'm not answering your questions, feel free to push back.
No, you're nailing it. This is great.
Right.
We're happy to be sitting next to the fire with Will today. Awesome. So my next question is, what needs to be in place to make sure a team is ready to take on a machine learning project? So if they're not doing it today, kind of as the framing of the question, what are the questions they need to answer as an organization, as a team, as a department, all those things to spin up doing machine learning based projects?
Yeah, I mean, I would say, unsurprisingly, I mean, it really depends on what your ambitions are, right? If you want to if your sights are set really high and you're like, I would like to, kind of change to what degree like my institution leverages this stuff, I would say you probably have at least 3 to 5 years of work ahead of you, if you're not already at this point, right? Okay. Of getting a really good handle on your data, right? That's it's almost like a non sequitur. Data scientists are limited in the value that they can be to you by like the value of the data that you have or the understanding of the data that you have.
Right.
And I'm talking about really like unsexy, boring stuff, right? Like have people that know, here are the data assets that the company have. Here's the systems, right? Have metadata about it. You would have no, maybe it wouldn't surprise you, but if I had a nickel for every time I asked for an entity relationship diagram for a database and got told like, what? No, we don't have that. I would probably not be working for Cargill or for anyone else for that matter, because I'd be a very rich man. And my subjective thing is just from my experience, like the more time that an institution spends on that stuff, like the faster you're going to accelerate into using advanced analytics to do better decision making, and the shorter amount of time you're going to go from just like having a bunch of data that you might not realize the value of, to the top of that maturity curve, right? It'll accelerate you down there, with obviously with the right talent, right? With the right, kind of people and the right vision. Now, you could find yourself in a situation where it's like, okay, I have these ambitions of like, changing how decision making is done with machine learning. I need to prove it out. I need to show some benefit to sort of talk people into making that investment. I would say in that case, your best asset is people. People who approach these things in what I subjectively and very biasedly think this is the right way. But data scientists who like are more like journalists than they are like crazy mad scientists, to paraphrase a tweet that I read and retweeted once a long time ago, right? People that like want to like dig into the details and get like the scoop on things, right? They have the skill set, right, to be able to analyze data and build predictive models out of these things, but are motivated by like finding out the right answer. And you get them in a situation, if you give and you can get them kind of like the keys to the kingdom, right? Get them access to the data that they need, connect them to the right people that can help them understand the data. Then you'll probably have some success. If you want to do it, sort of, if you need a couple of quick wins and you want like a couple of, good projects, I would say focus on the people. If you have a larger vision, at some point, you're going to have to focus on knowing and understanding the data, like your institution knowing and understanding its own data. I would say a lot better than the average institution.
Awesome. You know what's funny? Well, actually, my last question was on building teams. So again, okay, you are the ultimate mind reader. I know in our first advanced technology session, you spoke to ethics right before I was going to talk about that too. So you are just nailing it. So appreciative for your time and insights today. Those are all the questions I have. Are there any last words of encouragement or things you kind of want to mic drop moment with those listening in on about machine learning and Cargill's utilization of it? Anything you want to add before we wrap up?
Yeah. So I can say one of the things that I think is the coolest thing to me about this, and I should say like, so my background is in mathematics, pure mathematics. I kind of came to the field through a path that's, I'm finding not super common, but not totally out of the ordinary. I came through finance, and working, and specifically working for like insurance companies and financial institutions on the mathematical modeling of like risk, right? Insurance risk, credit risk, these sorts of things. It's the cool thing about data science to me, one is that like people come to it from lots of different backgrounds. Two, most of the tools that we use are open source, right? I mean, and for a long time that wasn't true. Like I remember kind of back, maybe 5 years ago in the industry that I was in, that industry, the banking and finance industry, we're just kind of like waking up to the idea that you didn't have to use SaaS for everything. And so a really cool thing is like that removes a big barrier to entry, right? Like you don't need a SaaS license to learn the coding, like the language skills that you need to be successful in data science, or if you want to be a machine learning engineer. Like, yeah, having a degree in mathematics or one of the physical sciences or in computer science, like that helps a lot, for sure. But also like the tools that we're using day to day, one of the coolest things to me is like anybody can download them, anybody can get online, start playing around with them. And so, yeah, so a word of encouragement, if it's something that you're interested in being a practitioner of, knowing more about, like get online, and start working through the many tutorials that are out there. get involved in something like Kaggle, the crowdsourced machine learning competitions sort of thing. You probably aren't going to win a lot of competitions, but one will get the experience.
Right. Build out your network too through using those too. That's a really good point. So basically what you're saying in some ways, Will, like the tools are out there. We need more data scientists. I know that for sure. That's one of the roles and spaces where we need more people. And you're saying there are some tangible ways to dive into it. If you don't have the background and you're not trained in it, it's not too late.
Yeah, absolutely not. I mean, you're going to need a good foundation of quantitative literacy to build on. I want to be clear about that. But also, and then this is going to sound like a plug. I have no connection with these people, but I can say the best book on the subject, it's actually free. So you can just go and download a PDF of it and read it. It's called The Elements of Statistical Learning. Cool. It was written by a group of people at Stanford. Also, Stanford has they're one of many institutions that have, a free certificate program and stuff.
Oh, that's cool. Awesome. Yeah. Well, Will, thanks for sharing your insights, and thanks to Cargill for sharing your wins and stories and challenges with machine learning with the broader tech community. We'll be better for it, most definitely. And if you have nothing else, we'll wrap it up. And I'm excited to share these insights with our tech community.
Okay, awesome.
Awesome. Thanks, Will.
Yes,
I'm going to stop recording, and then we can actually wrap up as humans.